I'm going to take these ideas that we've developed with this idea of solving for weak acid pH and apply it to the idea of solving for Ka, or determining what the Ka is of an acid. So when we get the ice table for a weak acid or a weak base reacting with water, we always end up with the same sort of algebraic expression, right? And previously we knew what the acid was, which meant we knew what the Ka was, and we knew what the initial concentration was, and we could use those to determine what the pH is going to be. And the pH is a description of what equilibrium will look like, what the concentration of hydronium is. But if we instead already know what that is, if we already know the pH of the solution, and we know the concentration of acid that we start with, then we can solve for this third variable being the actual, equilibrium constant for the acid, this dissociation constant, this Ka, which is characteristic of the acid. It identifies what the acid is, based on the value for the Ka. We have all those tabulated values that gives us that information. So we have these kind of three ideas that we can relate using this same equation setup that always is what comes out of an equilibrium constant, or the ice table that we use for our description of sort of weak acid equilibria in water, or weak base, when that reaction with water. And so we can apply it in some different ways, learn some different things about our solutions. Let's look at an example. The pH of a 0.350 molar solution of an unknown acid is 2.45. What is the Ka of the acid? pH of a 0.0350 molar solution of an unknown acid is 2.45. What is the Ka of the acid? So what I want to know is, what is the Ka of the acid? So we've gotten Kas before, and we can look them up on a table, right? So normally we would just go to our table. Here's our acid names. Here are the associated Kas. The thing is, we don't know what the acid is. It's an unknown acid. And actually, this is a common kind of process for determining the identity of an acid. Normally, we've used this table by, I know what the name of the acid is, what's Ka? But you can also go the other direction. If you know the Ka, you can figure out what the acid is. And so that's kind of the idea of what we want to do. We have information on pH. pH is 2.45. So that gives us information as to what the solution looks like at equilibrium, what the hydronium concentration is that we were previously solving for. And we also know what the solution kind of looks like from the jump. And so for the purpose of actually solving this, even though we are not trying to determine a concentration at equilibrium, we're still going to use an ice table type setup to figure out what's going on and to kind of set up the problem. So we don't know what the acid is. We know it's an unknown acid, but it's still going to react with water based on being an acid. So we know it's going to look something like HA. It reacts with water, and it makes A minus plus H3O plus. So you make the conjugate base and the hydronium. We don't know what it is, but the thing is, all acids react with water in the same way. They all react based off this. And we know that Ka is equal to the concentration of everything at equilibrium. We don't use water because it's pure liquid. And so if I could plug in these values, for right here, if I knew what all the concentrations were at equilibrium, I could plug in those values and then just solve for K. And so what we want to do is get these representations in terms of the variables, the algebraic expressions that we can get out of an ice table. So I don't know what the acid is, but I know I start with 0.050 molar. The water doesn't matter. Zeros and zeros on the product side. So this is kind of the standard ice table format that we have for weak acids. We know the shift is to products, and it's just plus X, because I'm dealing with a acid-base chemistry. 0.035 minus X. So I can now write this out as Ka is equal to I'm going to have the x's that plug in there. So I'm expecting to see the x squared, 0.035 minus x. So if I plugged in values, I'd be done. Now all I need is, what is x equal to? If I had a value for x and I could plug in that value for x, I'd be done. You may be tempted here. This is one of the places where we kind of veer off. We're not going to need to do an approximation because we're not going to solve for x using this. We can just use this equation. How we can solve for x is we can use the fact that the concentration of hydroniums is equal to x, right? That comes from the ice table. The concentration of hydroniums at equilibrium is just x. But we also have a pH. And so we also know then that the concentration of hydroniums is equal to 10 to the negative pH. So if we put these two together, we can get that x is equal to 10 to the negative pH. So x is equal to 10 to the negative 2.45. So we can use this relationship. This comes from our ice table. This is just generally true. The much same way that pH is negative log of the concentration of hydronium, 10 to the negative pH can give you the hydronium. So you can go back and forth between those two values. And so you can figure out what this value of x is based on the pH. The pH, and one thing that's unique and special about acid-base chemistry, is that pH lets us explicitly understand and know what equilibrium looks like. So in previous ice table problems, we were using ice tables to figure out what the concentration of hydronium was to be able to know what equilibrium was going to look like, and then what the properties of the solution would be when the reaction reaches equilibrium, namely what the pH is. In this case, we can measure the pH. That tells us what equilibrium looks like. So 10 to the negative 2.45, we get 3.55 times 10 to the negative third. And so what I can just do is take this value for x and plug it into that equation. And it's just 10 to the negative pH. And so I get, I'm going to shift over here a little bit to make some room. I get 3.55 times 10 to the negative third. That's all squared. And then 0.035 minus 3.55 times 10 to the negative third. And so those are all numbers. I can plug them all in. That is kind of tedious arithmetic, but it is still just arithmetic. There's no algebra to do. We don't need to make an approximation. We don't want to. We can get a better answer here by doing that subtraction. And we get that Ka is equal to 4.0 times 10 to the negative 4. And so we can use the fact that ice tables for acids all work out in the same way. It's the acid reacting with water to create the conjugate base and hydronium. And the values, kind of the algebraic setup, are all going to be relatively the same. And it's just a matter of then plugging in values on this side of the equation. And so previously, when we previously done ice tables, we have to get x from solving the algebra. But in this case, because I know something about what equilibrium looks like, namely, I know what the pH is, right? Because I know what the pH is, that tells me I know what equilibrium looks like, and I can plug in that value for x into the equation explicitly, and then I can go through and solve for what Ka is. And this can give me information as to what the acid that I'm dealing with is. When you take that value for Ka, so for example, we got 4 times 10 to the negative fourth. When you look at a tabulated values for Ka, you can find that number on there and see that that means the acid is HNO2. So this solution contained nitrous acid. And this calculation we just did is a really common way that we determine unknown acids. You can get the concentration of an acid using a titration, right? You don't need to know what the acid is to do a titration. You can just do the titration, figure out the concentration of acid because you know how acids react with bases. And so you can get the concentration of the acid, measure the pH using a pH meter, and then figure out from those two input values, determine what the acid is. And so this calculation is a really common method that we use to determine unknown acids based on the pH and the concentration of the acid. And so in this case, we figured out it was HNO2. Very nice. Participation 3-1, question 1. A 0.15 molar weak acid solution is found to have a pH of 4.76. What acid is contained in the solution? This is question 1 on participation 3-1 due Tuesday, March 1st at 11:55 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. Again, a 0.15 molar weak acid solution is found to have a pH of 4.76. What acid is contained in the solution? All right, first video down already have a participation question. Want to be on the lookout for the rest of those. We have our midweek due Wednesday, acid dissociation constants lab will also be Wednesday. You'll note this video was about acid dissociation constants. The lab is about acid dissociation constants. This video had a participation question. Acid dissociation constants, I think we will be seeing later in this semester. I think something we definitely want to be mindful of. But otherwise, we're just getting started here. See you in the next video.